Okay, so we had a nice little discussion on finite state machines. Let's move on to a basic processor design. The first thing we're going to talk about is the data path, which is how data flows through the processor. Once we have that down, we'll actually go to our next lab where you'll be designing different components of the processor, and then we'll be putting those components together in order to make a general purpose single cycle processor. Again, I took these from Dr. Gary Tyson. All right, quick recap. We had our finite state machine for the vending machine. It would work for a very specific case, but then if we want to make any changes, we'd have to replace it. So we want to come up with more of a general purpose situation. All right, so finite state machine, we had inputs and next state. Now what we're going to do for MIPS 32, we get rid of the inputs and outputs, and you just have memory and your register file, which has 32-bit 32-bit integers in it. Right. Now, this is just to say if you're going to try and make a ROM for this, it's not going to happen. Because you have more bits, more atoms than are in the universe, at least by our current calculations. But notice there's no inputs and outputs. How could we interface with this system via keyboard? Ooh. I mean, this is how our systems work. But we can still do keyboard things. We're missing a wire here. I'm being a little hidden. Where do you think the wire comes in? It's not coming up here. What is it probably manipulating?
Memory.
Memory, yeah. So normally when you hit something on the keyboard, it gets written to memory, and that's the state that goes in to your processor. So that's how interaction works nowadays. Yeah, it's input kind of, but it's just writing to the state. All right, good old Pentium processor. Wow, where do you y'all have got to be around early 90s, maybe? All right.
96.
96. Wow, so this was right before y'all were born. Whoa. Okay.
We're older. Oh, no, we're younger.
All right, so we're not going to even be able to get to explaining the Pentium processor because it's far more complex. If you take advanced computer architecture, you'll go through Pentium and all the way up to modern chips.
Is that a graduate course?
Yes, advanced computer architecture. Yeah. And I'm teaching it this semester too. But yeah, we go through this all the way up to modern chips.
Does somebody else normally teach it?
No, I normally teach advanced computer
Yeah,
architecture.
I think it's also an elective.
Oh yeah, you can take advanced computer architecture as an elective if you wish, as an undergrad. So you can have elective credit if you wish to do that.
That's not elective.
Oh, what?
Nothing.
You don't think that's an elective?
I mean, I don't know if I'm taking a graduate course as an elective.
Jonah, I don't think you have high enough aspirations in life.
I'm just saying.
Okay, let's go look at this picture. This one's actually, the nice thing about this one is it was labeled pretty well. Let's see, state. All right, we're going to highlight it. So you have registers. All right, guys. Registers. And those are very basic, or very simple memory. You usually only have 30, for MIPS you have 32-bit registers. In the Pentium processor you had 8 32-bit registers, which were right here in your register file and the logic around it. You had memory for your instructions, for your data. This of course was connected to even a bigger memory outside the chip. You had control. Now we'll go into what all that does about, hey, how do you take your current instruction from code, how do you execute that instruction? What does it actually mean to us is what this is doing. And then you send it out and have it worked on. Superscalar, and we're not going to be able to get a superscalar. Well, we might be able to. We'll touch base on it real bit, briefly. Superscalar, aka the execution of it.
I just like the name.
Superscalar? Superscalar out of order. Okay.
Parts.
So our building blocks for MIPS 32. By the way, your next lab, which I guess I was supposed to assign today, but I probably won't.
Okay.
Your lab's due tonight, is that right?
Yeah.
Yes.
Okay. Yeah, we got all messed up with the snow. Here are the building blocks. We haven't talked too much about memory. We've talked about muxes. We've talked a little bit about ROM. We've talked about, well, we've talked about half adder, but we really haven't talked anything more about that. But these, I'm saying, are the basic building blocks of a processor. You basically wire them up correctly, and you have a processor. Hey, look, okay, I just give it to you.
Yay.
So, this is going to be the overall look of a MIPS32 data path implementation. All right, keep in mind, MIPS32, we haven't talked about too much, is assembly for a MIPS processor, not an x86 processor, but a MIPS. Why am I doing MIPS? Because it's easy as opposed to the x86. Well, actually, x86 is easy, it just doesn't make any sense whatsoever. But MIPS at least makes sense. You know, it's like, all right, this is at least intuitive.
Good for learning.
Good for learning, yes. So, quick overview. Instruction memory, going to produce the instruction, which is going to be 32 bits long. Bits 0 through 15 go up here, 21 to 25 go there, 20 to 16 go here, or we got 20 to 16 also go here, as well as 20 to 10, 15 to 11. You don't know why yet, but we'll get to that. And the operating bits, which are the ones above it, go into this decoder, which activates certain lines down here, which are going to enable certain things to occur and disable other things from occurring. All right, that's the basic idea of this decode part. Let me see if I take other things down. Good. So let's go ahead and look at the different pieces, because there's a lot of pieces up here: muxes, an ALU register file, PC, and then some adders. So we need to actually sit down and start breaking this apart. So a mux connects one of the inputs to output based on the value selected. So there's the if. If select is 0, then the out is in 1. In other words, I get to write on the board now. Let's say select was 0, in 1 was 1, and in 2 is 0. Out would be 1. Oops. I need my mark. All right. Jonah? But if my select was 1, my out would be 0. All right. Okay, we're good.
Yeah.
That's a 2-to-1 mux. Decode. Oh boy. All right. Notice that the output has 64 bits. I'm only showing you the first 7 because I don't have time to write that all out. But notice that you have 6 in to 64. So 6 input bits activating one of 64 outputs. So if it's 0, you activate the 0 line. If it's 1, you activate line 1. If it's actually, if it's 0, you don't activate anything. I take that back. 1 activates line 1. 2 activates the second. 1, 1, aka 3, activates line 3, etc., etc. All right. ALU is just a representation of some function. So if I had input of 23 and 10 and my function was add, my output would be 33. Okay. Haven't talked about how it does that. I'm just trying to give you a high-level view of what it does. Because you could also do and. That might be hard to depict what this is, so let's go ahead and give it some bits. And the output would be
1,
1.
0, 1.
And.
Oh, wait.
Oh, I'll call it bitwise and. How about that? Bitwise and. That'll help you. So now it's
1.
It's just 1. 0, 0, 0, 1. If it was bitwise and I had this, what would the output be?
1, 0, 0, 1.
So you're just taking whatever spots have the same.
Yeah, it's bitwise and.
I don't understand that.
So take the first 2 bits, bitwise and. Take the first 2 bits, and them. That's your 1. Take the next 2 bits, and them. That's 0.
Got it.
Yeah, there you go. If it was a bitwise or, what would be the answer?
1 1 0 0.
Yeah, there you go. 1 1 0 1. Doing okay? All right. We also have an adder which just directly adds things. So 10 and 4 adds it to 14. Whoa, magic. All right, ta-da. Yeah, by the way, the function can be add, nor, equals. It can be a ton of different operations in your ALU. Sign extend. All right. This one might be a little confusing at first, especially since you don't quite understand why it's needed. But let's say your input, and I'm going to work with 4 to 8. All right, 4 bits to 8 bits instead of 15 to 30 or 16 to 32 bits, just to make it easy. So if you have 0 0 0 0 and you want to represent that as 8 bits, that's just 8 zeros. That's what it's doing. It's taking a small bit number and representing as a larger one. All right. If you had 0 1 1 1, that would also be 0 0 0 0 0 1 1 1. All right. Everyone see it so far? Here's the trick. If you have 1 1 0 0, it then extends it to 1 1 1 1 1 1 0 0. So it's really just taking whatever bit is this and copying it that way. All right?
What was that taking whatever bit?
Taking the bit, most significant bit. In this case, we're using a little Indian. So it's the most significant bit is the first bit, and it's just going to copy it over.
What do you call it?
Little Indian versus big Indian. That's with an E, not an I. Little Indian. You know, watch Gulliver's Travels with the, yeah. Do you remember I forgot which one it was, where they were fighting a war over which side to open their egg, on the little Indian side or the big Indian side? So yeah, they were fighting a war over, yeah. Right, it's making fun of war, right? But yeah, that's where this came from, because yeah, which type of Indian are you? Oh, you're a little Indian? Oh, well, I'm a big Indian, therefore I'm going to kill you. Yeah, stuff like that. Yeah. So little Indian, the least significant bits over here. Big Indian, the least significant bits over here. So it's basically, we are little Indian because 123, that's the least one. But to write this in big Indian would be 3 2 1, because there's the least. Yeah.
Yeah.
Okay.
It's an egg.
All right. Useful for computing unit when it's wider than data. Man, we are cruising. Yes. No question. Register file. Let me erase this. Small, fast memory to store temporary values. It's going to hold 32 integers, or 32-bit integers. So, inside of this register file, there is an array, ... of 32 integers, each which are 32 bits. Okay? These two specify which one to read. I want you to read registers 1 and 4, and the out would be the data value. Maybe register 1 had the value 32, and the register 2 had the value 100. Okay? You tell it which register you want to read, it produces what the values of those registers are.
So already programmed registers.
Mm-hmm. Maybe an example. All right. So if
Like an array.
0, what?
It's like an array.
Yeah, it's an array. It's literally an array. 32, 64, 81, 2, 3, and then 100. Of course, dot, 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 dot. So obviously it goes, okay, 1, we're going to index 1, that's 32. 4, going to index 4, that's 100. Okay?
Okay.
Write tells you what address you want to write to. Let me go down to the bottom. And let's say that this was 2. Let's say we're writing to register 31. Remember, 0 to 31. So register 31 is actually a 32nd register. And we want to write the data value, we'll say 5. So that would cross the 2 out and put a 5 there. Only if the write enable is true. So if write enable is true, you want to write to register 31 the data 5, then it would overwrite it. If write enable is 0, then of course this would stay as a 2.
They'd be like, no, you're not changing. They'd be like, no, you're not changing.
Yeah, this is just, do you do this or not? Are we actually writing to it or are we not? Because you have to have these wires are always going to be activated throughout your processor, so you need to signify whether they're actually valid or not.
So if you have a write enable,
Mhm.
you're going to take your signal from W1 and read it in, write it.
Okay, the read always happens because the read's not going to do anything bad, right? You can always read the value and spit it out. You're not changing your state. So there's no read enable if that's what you're getting at. But you have to know whether we are actually writing to the register file or not.
And what was D1 again?
That's the data that you're writing to register to the right register. This is where
that's
you're
the
writing,
register,
this is what you're writing to it.
And then reading up there is just,
These are where I want to read from. These are the values from those locations.
so 2 registers.
Ta-da! All right. Oh, wait, yeah. We good? Yeah. Memory. Whew. This is somewhat intuitive. The address you want to write to, 04A.
Sure.
The data coming in, data coming in, probably 32.
I think it says data in.
Yeah, that's data in.
Retain.
Write enable, are we writing to it and then are we reading? So this might be a little confusing. If this bit is 0, then we are reading from this address and ignoring data, and it's going to read out whatever values at that address. I don't have time to write this all out, memory's really big. If we are writing and it's been enabled, then we write 32 to that address. But if it's disabled, then this is don't care. Undefined. You'll see the reason for this later on when we put it all together. Because we want to be able that we can just turn the memory off whenever we want to and make it simple. Okay. Notice there's 2 memories, the instructions and the data. And for our chip, we're only going to have 64K words. A word is 32 bits.
It's a lot of bits.
A lot of bits. Okay, so our first MIPS 32 processor is going to be a microprocessor with interlocked pipeline stages. We haven't talked about pipeline stages because we're not going to do it right now. It's for our programming projects and it is very simple. Okay. I realized I should have done assembly before I talked about this, but that's all right. We'll keep going. All right, R-type instructions. How do we? The question is how now. Let me pause the video.